Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today we're delighted to have Robert Masson from UBC, who'll tell us about random walks on the two-dimensional uniform spanning tree.
Thank you, Yuval. And thanks very much for inviting me to Microsoft for this week. It's been a pleasure so far, and I'm sure it'll be a pleasure tomorrow as well. Okay, so as Yuval mentioned, I'll be speaking about random walks on the 2D uniform spanning tree, and this is joint work with Martin Barlow, who's also at UBC. So I think a lot of you, perhaps all of you, know what the uniform spanning tree is, but I don't want to lose anybody, so I'll review this very quickly. So we just have a graph. A spanning tree on a graph G is just a subgraph of G. That's a tree and that contains every vertex of G. So here's a graph. Here's a spanning tree. And if your graph is finite, then it's pretty easy to see that you can define a uniform spanning tree, which is just a probability measure that gives equal weight to every spanning tree on the graph. So if your graph is finite, there are finitely many spanning trees, so this is easy to define. If you want to look at uniform spanning tree on infinite graphs, P. Mantle showed that, well, this is more general, this is not only in ZD, but in particular, if you want to look at the uniform spanning tree on ZD, you just look at the uniform spanning tree on finite subsets that increase up to ZD, and P. Mantle showed you can take a weak limit and that this is well defined. So in general, you call this weak limit the uniform spanning forest because it's not necessarily connected. So for dimensions 5 and higher, it's not connected. For dimensions less than or equal to 4, it is connected. And you can call it, therefore, it makes sense to call it the uniform spanning tree. So for the rest of the talk, we're going to focus on the two-dimensional case. So we'll let U be the uniform spanning tree on Z2.
Wait, this should be question, why is it not connected in high dimensions?
I mean, one of the ways to see it is essentially that if you take two random walks, they won't, in dimensions 5 and higher, they won't intersect, essentially. Or they're, sorry.
If you take uniform spanning tree in the large box, you look at the path between two neighboring vertices. In dimensions 5 and higher, it turns out, it's not trivial, that the path between them gets longer and longer, typically, and so in the limit, it could disconnect.
So for any finite size, it's connected.
For any finite size, it's connected, right? When you pass the limit, it can break up.
Okay, so here's just a simulation of the uniform spanning tree on Z2. So this is actually a window, which is why you notice, that it's not connected. This is the uniform spanning tree on the entire plane, and we're just going to look at I think there's a 50 by 50 window of it. Okay, so there's a strong connection between uniform spanning trees and loop race random walks. And I know I haven't defined the loop race random walk. I'll give a more precise definition in a second, but it's essentially what you think it is. So given any two vertices in the uniform spanning tree, there's going to be a unique path between them. And we're going to let gamma VW be this unique path. And P. Mantle showed that the distribution of this path is the same thing as running a random walk from V to W and then loop erasing. So this is true in certainly any finite graph, and is also going to be true at least in Z2, because because it's recurrent. More generally, Wilson, there are actually other algorithms, such as the Aldous-Broder algorithm, which generates spanning trees with this idea of running random walks and loop racing in a certain sense. So the algorithm we're going to be most interested in is Wilson's algorithm, which allows us to construct uniform spanning trees by running loop race random walks. So instead of writing anything down, I'm just going to describe this with, I think, with a simple example here. So if we want to construct the uniform spanning tree on this graph, first of all, we just take a point, whichever one we want. And this is going to be kind of our first tree. Our first tree is just going to be consist of a single vertex. For the next step, we just choose any other vertex at random. Then we run a loop erase random walk from the second one to the first. So first of all, we run a random walk from this vertex until it hits this one, and then we loop erase the path. I'm not going to show the random walk, but this is, for example, what you might get after you loop erase. Then for the next step, you just take any of these 4 remaining ones at random. You can actually choose them depending on what has already happened, which is interesting. So let's say we chose that one. Again, we run a loop erase random walk until we hit the tree that we've already constructed. Finally, we're left with the last one. We pick it. We run a loop erase random walk. We get something like that. This, of course, gives us a spanning tree. And you can show that all spanning trees are equally likely. So we get the distribution of the uniform spanning tree. OK, let me give a more precise definition of the loop erase random walk, just because I need to introduce some notation. So again, we're just going to be interested in Z2. You can, of course, define loop erase random walks pretty much anywhere it makes sense on any graph, say. Let S be a simple random walk started at Z in some subdomain of Z2. We'll usually let Z be the origin, but not necessarily. Then just this notation, we're going to let sigma D be the first exit time of D. So we run the random walk up to the first time we exit. Then we erase the loops chronologically. And we're going to denote what we get by, so L is just a loop erasure of the random walk from time 0 up to sigma D. OK, here's just another simulation from 0 to the circle of radius 100.
Seems like it's always the same picture. It's almost like this random walk is deterministic.
Well, what's interesting, I've noticed with simulations, is once it seems to have picked a direction, it just goes in that direction. It doesn't really, mess around too much. Once it's kind of decided where it wants to go, it goes there pretty quickly. It would be interesting to actually quantify this, precisely and prove something like that. But when you draw these pictures, you notice it really always kind of stays on one little part of the circle, more or less.
Prove the opposite.
Well.
That once it picks a direction, if you wait long enough, it will change its mind and will go in another direction.
Well, how long do you have to wait, I guess? Yeah. OK. Well, so this is a notation I really needed to introduce right here. So we're going to let mn be the number of steps of the loop erasure of the random walk from 0 to sigma n. So sigma n is just first time it leaves the ball of radius n. And the major theorem, which was first proved by Kenyon in 2000, then in my thesis, I proved the same thing using a different technique that was valid for any discrete lattice in the plane, is that the expected number of steps of a loop erase random walk from 0 to the circle of radius n grows like n to the 5/4. So the precise statement is that these two things are logarithmically asymptotic. So an interesting open problem, which people have certainly thought about, and I don't think much progress has been made, is to show that the expected number of steps is actually comparable to n to the 5/4. So of course, in this statement, this logarithmically asymptotic statement, you could have that E of mn was n to the 5/4 times some log factors. But certainly everyone believes that there shouldn't be any log factors and that these two things should be comparable. Mm-hmm.
Just for curiosity, what would be the value if you didn't take out the loops?
Just a random walk?
Yes.
That would be n squared.
Okay.
So random walk from 0 to that would grow like n squared. And that's definitely known up to, asymptotic. One knows very, very precise estimates for that. I guess I should mention this. I didn't prepare any slides, but so this is 2 dimensions. This is definitely a 2-dimensional result that it grows like n to the 5/4. 3 dimensions, the existence of this exponent is not known, but we believe it exists. And I think David Wilson has done many simulations in this, and he could tell you the exact value that that he believes, or that the simulations tell him. And there's no reason that in 3 dimensions you'd expect this to be a rational number, any sort of nice number. I think he was 1.62 something, I think he was mentioning. In dimensions 4 and higher, it will be 2. It'll be the same as the random walk. Essentially, when you get to high enough dimensions, you're not really creating very many loops, and you're going to get the same growth as just a random walk. Okay, this notation, this is to remind me to write this down. So I'm going to be using these capital G and little g throughout, and I just want to write this down just so you know. So unfortunately, if we knew, essentially I'm going to get a bunch of results that have this, that are, some quantities are comparable to something involving capital G and little g. If we knew that these things were actually comparable to n to the 5/4 and comparable to n to the 4/5, I wouldn't have to bother with this notation. But unfortunately, since there might be some hidden log terms in here, I'm going to use that notation. But whenever I use it, you should just think that capital G is n to the 5/4 and little g is n to the 4/5. Okay, so now let's get to the main part of the talk, which is random walks on the uniform spanning tree, for which is just the last little bit of notation I have to introduce. The first notation, I think I've already introduced it. Gamma xy is just a unique path between x and y in the uniform spanning tree, or equivalently, you can think of it as just a loop race random walk from x to y. We're going to let d be the intrinsic metric on the uniform spanning tree. In other words, the distance between x and y is just the length of the unique path between them. BD of xr is just the ball of radius r in that metric. The cardinality of BD xr, well, is just what I said. It's the cardinality. It's I'm going to be using the word volume of BD xr. It's just a number of points in that ball. And finally, if I don't have a subscript, we're just going to BXR is just a usual Euclidean ball. All right, so here are a few simulations. This is BD040. So I didn't really mark off where the origin is, but the origin is somewhere, well, it's exactly in the center of this picture. And these are just, in red, are just the vertices that are at distance less than or equal to 40 from that in this simulation, or this instance of the uniform spanning tree. Oh, so sorry. This is kind of the nice, a nice picture. This is, in some sense, what one would expect or one would hope, which is that, you know, this looks roughly, well, not exactly, but it's somewhat, it's not too strange. It's a Euclidean ball that's a bit deformed, but not too far from a Euclidean ball. Some of these other simulations tend to be not so good. This is a bit of a stranger set. And this is also somewhat strange in the sense that the origin is somewhere here, and it seems like all the points that are less than or equal to 40 are all lying on one side. But a major part of this talk is going to be talking a little bit about what these sets look like or should look like. Unfortunately, at least with my kind of weak laptop, it's computationally pretty expensive to generate very large instances of these things. And
Looks like a neck.
yeah, it's pretty slow. It's not even very good for browsing the internet. So generating huge uniform spanning trees is not, you know, it's not very happy about that. But if you generated these, I wish David Wilson was here so I could ask him to do it, since I'm sure he would be the best person to do it. But hopefully, if one generated enormous uniform spanning trees, and one looked at these sets, so BD 0, 10,000 or something. Well, at least if you believe the theorems I'm going to be telling you later, these should look roughly like Euclidean balls in some sense. I'm going to give you a precise statement of what I mean by that very shortly. Okay, so now let's look at at random walks on the uniform spanning tree. I guess I promised that I had finished with the notation, but it looks like I have a bit more notation. but you can probably guess what these things are even if I didn't tell you. So Pn of xy, these are just the transition densities, so probability of a random walk on the uniform spanning tree starting at x, probability that it'll be at y after n steps. Oh, so what do I mean by random walk on a uniform spanning tree, just so everyone's on the same page? I mean, we have two levels of randomness here. We have the randomness of the uniform spanning tree. We generate a uniform spanning tree. Then given a uniform spanning tree, we just do random walk on that graph. So just simple random walk. You choose the next step. You visit each of your possible neighbors with equal probability. So Pn are the transition densities. Tau r is going to be the first time you leave the ball, the graph metric ball of radius r, and tau tilde r is the first time you leave the Euclidean ball of radius r. And so the major theorem in this talk, or in our paper, is just estimates on all of these quantities. So we actually have various versions of these, kind of quenched, annealed versions of various precision, but I don't want to go through all these details. Essentially, one just has that Pn or P2n so the return probability grows like n to the minus 8 over 13. The first time you leave a graph metric ball grows like r to the 13 over 5. First time you leave a Euclidean ball grows like r to the 13 over 4. And finally, if you just look at the furthest you've been up to time n, this grows like n to the 5 over 13. I don't expect you to remember all these quantities. There won't be any tests or anything. So you're welcome. But maybe if you wanted to remember one result, this is probably the easiest or the best one to remember, is you can talk about the spectral dimension of an infinite graph. So given an infinite graph, if you just let Pn be the transition densities, transition probabilities, the spectral dimension of G is just minus 2 limit as n goes infinity log P2n over log n. The reason I have P2n, right, is because of bipartitism. So what is this? Well, first of all, notice that the spectral dimension of ZD is D, which is always a good thing. And in some sense, this just measures how recurrent or how transient your graph is. The smaller this value, the more recurrent your graph is. So and
Exactly as n here, is it the number of nodes?
n is just, no. Yeah, the probability of being at the origin after 2n steps. So there's been kind of some recent interest in spectral dimension. I just want to highlight one thing since there's a Microsoft tie here. Gadi Kozma and Asaf Nachmias proved that the spectral dimension of the incipient infinite cluster for critical percolations in high dimensions is 4/3. So high dimension, I think it's d greater or equal to 18. Is that right? 19, sorry. Which is the Alexander-Orbach conjecture. So that's for critical percolation. So if you remember in the previous slide, I had that P2n growed like n to the minus 8 over 13. So if you just plug that into this definition, you immediately get that the spectral dimension of the uniform spanning tree on Z2 is 16 over 13, almost surely. All right, so where do all these quantities come from? And they essentially come from two sources. They come from volume estimates and effective resistance estimates. So let me talk a little bit about what that means. Let's just talk about random walk on a graph. So right now there's no randomness. Let's just fix any graph, infinite connected graph. Let's suppose, so G is sufficiently regular. I want something like strong recurrence, locally finite, and a volume doubling property. I think that should be enough. But I'm just speaking on very vague terms, so don't ask me for any sort of very specific details. So suppose you know that G is sufficiently regular. Remember, this is the volume. Suppose you knew that the volume of the ball, so the graph distance ball of radius r grows like r to the alpha, and the effective resistance between the origin and the complement of that ball grows like r to the beta. So what is effective resistance? I mean, I don't want to talk about so much about that, but just put a unit resistor on each edge and just look at the effective resistance, I guess, between the origin and the complement of this ball. Anyways, I don't think about these things so much. In this case, this is something that I like to think about a lot. It's kind of dying. The way I think about it is that in this specific instance, the effective resistance between the origin and the complement of the ball is the same thing as the Green's function for the random walk in the ball of radius 0r at the origin. Is this thing really dead? Oh well. Then if you know these two facts, this kind of tells you pretty much all the basic things you want to know about your random walk on the graph. The return probabilities are going to grow like n to the minus alpha over alpha plus beta, and the expected time you leave this ball of radius r is going to grow like r to the alpha plus beta. So I quoted this paper, but I'm sure this must have been, things like this must have been known before that, I guess. This paper kind of laid down, it laid down some sort of precise statements of this fact. But I just want to give you a vague intuition of where this is coming from. So how does knowing volume growth and effective resistance growth tell you things about your random walk? So again, I'm being very informal here. But if we want to look at this quantity, the expected amount of time it takes to leave the ball of radius r, well, this is the same thing. So this gr0y, this is the Green's function in the ball of radius r. So the expected time it takes is just the sum over all the points in the ball, the gr0y. You can rewrite this Green's function gr0y as gr0 times the probability starting at y that your random walk hits 0 before leaving the ball. Remember it's basically dead. Remember gr00 is just this effective resistance term, so I pull that out. Then we're just left with the sum over all points in BD0R times these probabilities. Well, I claim that that is comparable to this volume term. Certainly these probabilities are less than or equal to 1, so this is certainly less than or equal to the number of points in BD0R. But this is also going to be greater or equal to the sum over all, oh, it's alive again. The sum over all points in BD0 R over 2 times these probabilities. And then here you're assuming some sort of regularity. If your graph is nice enough, then if you're sufficiently close to the origin, say within BD0 R over 2, these probabilities should be greater or equal to some constant. Finally, you use some sort of this volume doubling condition to get that sum would be comparable to this volume term.
I missed the last point. You said if you're within R over 2, the probability you hit 0 before leaving.
Yeah, shouldn't that be true?
In which means.
Oh, right. It's
not true in Z2.
Yeah, that's true. That's not true in Z2. If you have strongly recurrent, that should be true, right?
Right.
But I think I did mention we were assuming strongly recurrent. But it is true if it's strongly recurrent, yeah. Okay, so we're assuming G is strongly recurrent.
Was it in this? Can you flip back to where the state
Yeah, I think they assume that. At least one of the statements. I mean, they had very many different statements.
It wasn't stated here.
No, I know. It was in this sufficiently regular thing, which is
Z2 is pretty regular. So strongly recurrent is different from regular.
Okay.
Okay.
Z2 is not regular. The resistance grows not.
Right, but
that's true. Yeah.
The term regularity.
Well, but then if it's sufficiently regular and this is true, but I guess that wouldn't be true for Z2. So. Well, anyway, I was being very informal there. But this next statement is going to be even more informal because there are no equations here. So that gives you this why this first term, at least some idea why this first term grows like r to the alpha plus beta. So what does that tell us about these return probabilities? So this is very rough and informal. So if we let 2n or n be r to the alpha plus beta, then with high probability our random walk after 2n steps will still be in the ball bd0 constant times r, since it's taking this long to leave the ball of radius r. This has this many points based on our assumption about the volume growth. And so the average value on this ball will be n to the minus alpha over alpha plus beta. Again, given enough regularity on G, this average value should be close to PTN 00. So that's why, hopefully this gives you a rough idea where these quantities are coming from. Because I kind of hate it when people just lay down these theorems with these kind of precise statements and give you absolutely no idea where anything is coming from. But the take-home thing is that, if you know things about effective resistance, if you have precise estimates about effective resistance, about volume growth, this tells you a lot of things about your random walk on the graph. Okay, so that was for a fixed graph. If our graphs are now random, then you get the same results, assuming you can prove things with high probability. Again, I don't want to go through the exact statements of what I mean by with high probability. I'll give you the precise statement of what we're going to need for the uniform spanning tree. But if you have these estimates with high probability, then you can get, again, with high probability, you can get good estimates on your random walk on your random graphs now. So for the uniform spanning tree, we have roughly, and I'll make a precise statement of that, we have roughly that with high probability, our volume grows like r to the 8/5, and our effective resistance grows like r. And so if we assume that for a second, we just plug that into our previous results, which tells you how to get information about the random walk from these estimates. I won't do it, but if you remember what the theorem stated, that tells you where all those exponents for the uniform spanning tree came from. The 13 over 5, 8 over 13, etc. It just comes from these two facts, that we have volume growth like r to the 8/5 and effective resistance growth like r. So what is the precise statement for these volume growth and effective resistance growth? Well, this is the precise statement. So there exist these constants such that for all lambda and r, the probability that the volume of BD0R is between lambda g of r squared. So remember, g of r was logarithmically asymptotic to r to the 4/5. So just think of it, this is essentially r to the 8/5. So the probability that this volume is between these two quantities, the probability that it's not decays exponentially in lambda. And similarly, we get a similar statement for the effective resistance. Note that there's no lambda here because this is a trivial bound, or this is a bound that will hold for any graph that is less than or equal to r. So we don't have to put a lambda for this upper bound here. The other thing I want to point out is don't pay so much attention to these exponents. They're certainly not optimal, and the ones I'm quoting here are possibly not even the best we could do if we really cared about getting the absolute best exponent here. In general, when I have exponential decay, I'm not going to care too much what the exact exponent here is. Okay, so I don't really want to say too much about the effective resistance bounds. In some sense, this is the easier and less interesting one. So generally, if your tree is nice enough, you would expect a linear growth for the effective resistance. And so maybe you can correct me if I'm wrong, but if you have a tree and so obviously this is not going to hold for a binary tree or something like that, but if at depth r you have at most r to some power leaves, would you expect a linear growth in the effective resistance? Or it's more
critical trees. I think if you look at the path from the origin to level, the path to level R, you have many paths, but most of them agree up to the first R over 2 or R over 10.
Mm-hmm.
That guarantees.
Okay.
If you had polynomial growth, but you had a lot of branching early, then the resistance would.
So sometimes you just don't want too many possible branches out to distance R. Yeah. But certainly for our uniform spanning tree, we expect that. And in some sense, the proof of this kind of comes out of, the next theorem I'm going to state. So for the remainder of the talk, I'm really going to focus on this first thing, which is showing this volume growth. And in fact, we're going to show something somewhat stronger, which is actually describing what this graph distance ball looks like. We want to state that it's roughly like a Euclidean ball of radius g of r. So g of r is r to the 4/5. In other words, the probability that BD0R is not a subset of B0, g of r times lambda, decays exponentially in lambda. The probability that the Euclidean ball of a smaller radius, lambda inverse g of r, is not in BD0R. Well, okay, in this case, we actually have polynomial decay. So this result, of course, does not follow immediately from this theorem. The upper bound will, because we have an exponential decay here. But of course, here, since we have polynomial, we can't immediately get exponential here from this polynomial one. So to really prove this, you need to do a more complicated argument. Use this lower bound and kind of iterate this result to actually get an exponential decay here. I'm including this lower bound, this lower bound to show that you actually cannot do any better than polynomial decay for this lower estimate. So even if we hoped to get exponential decay, we actually cannot do it. Again, these exponents are not optimal, or there's no reason for us to believe that these exponents are optimal. But when I have polynomial terms, I actually am giving you the best exponents that we have. So we made some efforts to get the best possible exponents that resulted from our arguments. And so these are the best possible ones that we have. But there's no reason to believe they're optimal. Okay, so let me give you some heuristics of why you would expect this BD0R to be roughly like the Euclidean ball of radius little g of r. And this is very rough, and don't interrupt me because I know this argument is flawed. But hopefully some of you might see why this is flawed. But here's a very rough idea why you might expect this to be true. All right, let's fix some z and z2. And we want to look at the distance from 0 to z. So that's just the number of steps of the loop ratio of a random walk from 0 to z. Roughly, we'd expect that with high probability, this d0z should be close to its mean. I mean, one can always hope that a random variable will be close to its mean with high probability. And then, well, what's this? Well, we're at distance absolute value of z from the origin. We're looking at, in some sense, a loop race random walk from 0 to z. Well, we should hope that that's roughly capital G of absolute value of z. Remember, capital G, this is just E of mn. This is the expected number of steps of a loop race random walk from 0. Hopefully you guys can see, maybe not. Well, I won't write anything more, or I don't plan on writing anything more. But capital G is just the G of absolute values. Z is just the expected number of steps of a loop race random walk from 0 to the circle of radius absolute value of z. So you can hope that that should be roughly that quantity. And so we'd expect that with high probability, z is in the ball of radius 0R, z is in BD0R if and only if g of absolute value of z is less than or equal to r, which is if and only if z is in the Euclidean ball of radius little g of little g of r. Okay, but there are a lot of things that are wrong in this argument. Perhaps the most striking one is that this expectation is actually infinite, so it's going to be difficult for us to be close to the mean. So this is I think this is a very striking and very interesting fact. This was proved by Benjamini, Lyons, Perez, and Schramm, which is that, so there's a slight generality of that, but essentially the same proof. For all z besides the origin, the probability that the diameter of this unique path from the origin to z is greater than n times absolute value of z is actually greater than 1 over 8n. So of course, if you sum up over all n, you actually end up with something infinite. So I find this very striking. Even if z is a nearest neighbor to the origin, the expected length of the path from 0 to z is actually infinite. So it's going to be hard to use this first part of the argument that d0z should be close to the expected value d0z. And there's another difficulty which is perhaps less, there's a difficulty, but it's not actually something wrong in the statement or anything. We're claiming that these balls are close to each other. So we need to, we can't just fix some z and show this is true. We actually have to show that this is true for all z simultaneously. In other words, we just need to kind of invert some quantifiers. Instead of showing for all z with high probability this is true, we actually have to show that with high probability for all z that's true. So we'll deal with these difficulties one at a time. So what we're going to do is use Wilson's algorithm and combine with very precise bounds on the probability that the number of steps of a loop race random walk deviates from its mean. So hopefully the goal was, I don't know if I succeeded, but the goal was trying to convince you that at this point in the program, so when we're looking at these volume growth, looking to prove this volume growth estimate, hopefully I've convinced you that it's going to be very useful to get very precise estimates on the number of steps of a loop race random walk. And we need to know a lot more than just what its mean is. We really need to know, have very precise estimates on how close the number of steps of a loop race random walk is to its mean, to n to the 5/4 or whatever, or e of mn. Because when we're constructing the uniform spanning tree, we're not just constructing one loop race random walk, we're constructing a whole bunch of little loop race random walks. And so we need, in some sense, we need all of them or most of them to really have the number of steps that we expect in order to say anything about the uniform spanning tree. It's not enough just to know, the expected number of steps of each of these little loops, because if we have, these these unexpected number of steps, this can really mess up the way our uniform spanning tree is constructed. Well, luckily, we have these estimates, or we proved these estimates. So let me just tell you a little bit of how this project evolved. I started this project with Martin Barlow. We started trying to examine the random walk on the uniform spanning tree, and we essentially came to this point, the point that we're at in this talk, where we realized we really need these very precise estimates on how far mn deviates from its mean. So then we kind of we took a break from the uniform spanning tree, and we went ahead and we proved these estimates on the loop race random walk, and then went back to the uniform spanning tree and applied them.
And these estimates were well-known open problem separately.
Yes. Well, actually, if you really, really want to know the history of this, I was actually starting to think about this even before I went to UBC. Martin Barlow, we talked one day, and he was talking about the uniform spanning tree, and we realized, okay, we need these estimates, and it was some sort of miracle that I had already started thinking about these and had some results in that direction, and together we really, we really got very good estimates and precise estimates. I was looking at the second moment. We ended up getting exponential moments for these things. But here's the main result about the number of steps of the loop race random walk. So it's just looking at the tails of mn over E of mn. So this really just gives you the precise estimates we have. The probability that mn over E of mn lies between lambda inverse and lambda is greater than 1 minus some term which decays exponentially in lambda. Again, I'm not giving you the best exponent. You can take lambda to the 4/5 minus epsilon if you want. But when we're applying this to a uniform spanning tree, what we're going to be doing is we're going to be using Wilson's algorithm. We're going to construct part of the tree. Then we're going to go to the next step of Wilson's algorithm, which requires running loop race random walks until we hit that tree. So we need a bit more than just knowing. The previous result was this is just loop race random walk in the ball in the disk or in the ball of radius n. We need to actually get specific estimates on the number of steps of a loop race random walk in a more general domain when we're using Wilson's algorithm. And so we have the following two results in that direction. So the first one is essentially saying, well, I'll let you read it. We have this condition on a domain D. For all z in D, there's a path in the complement connecting, bz n plus 1 and bz 2n complement. Yeah, maybe I should do that. Really what this is saying is just that so here's our domain, and okay, I haven't given you a domain yet. Let's say, all right, this is the easiest example of a domain to draw. Let's say this is just a strip, an infinite strip like this. And this is height n. This would be an example of a domain satisfying that property. Because for every z in that domain, we're at distance less than or equal to n from the complement or from the boundary, and the boundary is sufficiently large. The main idea here is just that if you start a random walk at z, then with high probability your random walk is going to leave the domain within before going distance 2n away. This is really the only fact we need. You're not going to go too far away, or else your steps might become too large.
I understand the quantifier and the assumption about what is n.
Suppose there exists an n such that for all z, the following holds. So essentially, you'll take the largest n for which this condition is satisfied. So if this was our domain, I would obviously take that n to be equal to this, and that would give me the following estimate, because the estimate here depends on n. Okay, the second one is much easier to understand. The second one is just if D contains the ball of radius n, then the probability that the number of steps is small is going to be small. Okay, now let's see how we apply those results. So remember, I said there were two difficulties. I gave this very rough heuristic argument, which was false. And there are two main difficulties. The first difficulty was we're going to fix some z, and we want to show that with high probability, the distance between the origin and z is close to this capital G of absolute value of z. Remember, we saw the expectation of this was infinite, However, it's still going to be true that with high probability, and I'll make I'll say what I mean by with high probability in a second, we can still show that these two things are close. So what we're going to want to do is look at the probability that the distance between 0 and z is less than lambda inverse of g of z, and the probability that this quantity is greater than lambda g of z. So one direction is easy. It's going to be very unlikely that this distance is small. Let me draw. This first one can be easily explained with a picture. Okay. So we're at the origin. We have some point z, and we're running a loop race random walk from the origin to z. So the really bad thing that could happen is that the loop race random walk goes very far away before coming here. But for this first term, that's not going to affect the probability that it's too small. I mean, if anything, the bad thing is that the number of steps is too large. The probability that the number of steps is too small is really not going to be very likely. Essentially, you just cut this off at absolute value of z over 4 and just look at the initial number of steps. So the number of steps of the red part is certainly less than the number of steps of the blue part. And the distribution of this, so I've made a little lie. It's not going to be exactly m absolute value of z over 4, but it's going to be, you can deal with this issue. It's essentially the number of steps of a loop race random walk from the origin to the circle of radius absolute value of z over 4. But this term, this is exactly the situation that the theorem about the number of steps of loop race random walk was meant to handle. This immediately gives exponential decay in lambda. So the probability that the number of steps is too small is really not a problem. The difficulty is showing that the number of steps can't be too large. And again, it's these bad pictures where the loop race random walk goes very far away before coming and hitting z, which is why the expected number of steps is infinite. Well, we're not going to be able to estimate it directly. But if we restrict the path to stay in some sort of larger ball of radius lambda to 1/2 absolute value of z. So if we ensure that our loop race random walk doesn't go too far away, we actually can show exponential decay. So this doesn't follow what we did before, but you can believe me or not believe me and read the paper. Therefore, the probability that the number of steps is too large is less than or equal to, well, probability it's too large and that it stays in the ball plus the probability that it doesn't stay in the ball. And another thing you can show, this probability that it doesn't stay in the ball, you can actually bound by lambda to the -1/6. And so the second term dominates, and so you get a polynomial decay for the probability that the number of steps is too large. Okay, finally, and just a few more slides, let me show. So the second difficulty was, the previous result, we fixed some z, and we showed that the distance from 0 to z is about what we expect, which is, well, absolute value of z to the 5/4. Now, how do we deal with all z simultaneously? So there are two directions to show, but I'm only going to show one direction. And that's going to be that with high probability for all z in the Euclidean ball, the distance from 0 to z is less than lambda times, well, r to the 5/4. And this will imply that with high probability, of course, the Euclidean ball radius lambda inverse little g of r is contained in BD0R. So I have this condition at the top. So we want to show with high probability for all z in this Euclidean ball, the distance from 0 to z is less than lambda g of absolute value of r. So the step one is, and you.
The direction is easy, right?
No.
It's not.
It's
I mean, you
no.
get an exponential just by this argument, and the arrow of the z over 4, and the arrows that you get are exponential.
But you have to sum up over some number of points that depend on r.
Polynomial, and you get an exponential error.
But the exponential error is in lambda.
Can't you? If you know, can't you?
Well, Not easily.
Because you don't want to take lambda which goes within. So.
Yeah, I don't think you can do it easily. No, the other direction is actually very similar to. So what we're going to do is we're going to use Wilson's algorithm in a particular way. The other direction, you also use Wilson's algorithm in a somewhat similar but slightly different way. So don't pay too much attention about these exponents. I'll just highlight the main idea, and there'll be pictures. So what we're going to do is we're going to let D1 be a set of lambda to the 1 over 10 points in this set. There'll be a picture soon. Space, distance, r apart. OK, so we're interested in the points in this ball. We're going to look at a larger ball. And on the first step is we're just going to take some points that are spaced distance r apart. Then we're going to perform Wilson's algorithm. Oops. All right. Now perform Wilson's algorithm with those points. And you're going to end up with some initial tree, which we'll call U1. So do it. I mean, you can do it with whatever order. It's just you choose these points to do your first Wilson's algorithm tree. Then, if we let n1 be the largest distance from the origin on our tree U1, then the probability that n1 is greater than lambda g of r, well, it's certainly going to be less than the number of points in D1 times the probability that each point is greater than lambda g of r. This quantity is what we just determined was less than lambda to the, what did I say, minus 1 over 6 or something? And this, we had lambda to the 1 over 10 points here. The thing is just you choose these exponents in such a way that you then have a polynomial decay in lambda. OK. The next step, and ignore these things, the next step is just take a smaller ball here, and we're going to take, so we're going to have k iterations of this, and as k goes to infinity, these balls are going to converge to the Euclidean ball of radius r that we're interested in, and we're going to take these points to be closer and closer together. So eventually, when we do enough of iterations, we're eventually going to, all the points in this ball are going to be on the trees we've created. OK, so then we perform Wilson's algorithm. And the point is now that we've already constructed a tree, the probability that the distance from all our points in the kth tree to the k minus first tree is less than some quantity. Again, I'm just going to skip through this. But you can use these precise estimates on the number of steps of the loop race random walk to just look at the probability that the distance from z to the previous tree is large. And it's some term like this. Finally, we just perform this algorithm as many times as we need so that all the points in this Euclidean ball that we're interested in are eventually going to be in one of the trees. Then we just use all the previous estimates that we had. So the probability that there exists some z such that the distance is greater than lambda g of r is going to be less than this sum. It doesn't really matter what the sum is, but it's going to be exponential in lambda. So this first term dominates, and then that's the quantity we get. So it's really only the first term that's going to matter. The proof of the other direction uses a similar argument, constructing Wilson's algorithm in a precise way, and also using these exponential estimates on the number of steps of the loop race random walk. OK, but that's all I wanted to say for today. Thanks.
And so, first one question. So the spherical nature of the ball in this intrinsic metric. So at the end, you get it with or without logarithmic correction. So
Do you want me to go back to the theorem?
go back to that theorem. Because when they have the double wiggle,
but that one didn't have any double wiggles.
okay.
Oh, stop. I'm not doing anything here. This is my crappy network. All right. probably, let's see. Whoa, is this what we wanted? Wait, the next one. This is what we wanted, right?
So there's no logarithmic.
Well, it's little g, and you don't know what little g is.
Right, but
That's true, yeah.
But you know that it's a sphere.
Yeah.
So there is some intrinsic interest in it.
Yeah. Just if all you wanted was to get the exponent, then you could simplify.
You mean if all you wanted was this estimate, just for the volume?
I'm saying what I said before, if all you wanted was the exponent, the n to the 4/5,
Yes.
then you could take lambda to be polylog,
Yes.
because you wouldn't mind, and then it would simplify your proof, because you could take union bounds over the z's, right?
Yeah, yeah.
Okay.
Okay.
Any other questions or comments? Let's thank Robert for a wonderful